Okay, am I audible? Can you hear me?
Yes, sir.
Yes, sir.
Okay, thank you, Rohan. Okay, okay. So in the last class that I took yesterday, so the last class that I took yesterday, so I told that today I'm going to take an extra class. So today, yesterday in the yesterday's class, I have discussed what do you mean by the differentiability of a complex valued function, and I've discussed also how to check whether a given function is differentiable or not. After that, I've started discussing the analytic function. So I've given just the definition of analytic function. So just I'm summarizing that, then I'll start discussing how to check whether a given function is analytic or not. So can you see the PPT? Is it visible?
Yes, sir.
Okay.
Yes, sir.
So in the last class, I've told that compared to the differentiability of a function, analytic function is more stronger compared to the differentiability of a function. Okay, so differentiability means just we take we actually consider a differentiability at only one point, but analyticity at a function means we are not only considering the differentiability at that point, but around that point we are considering any neighborhood, and we are saying that the function being analytic at that point, the function is differentiable at all other points inside that neighborhood. Then compared to this one, the second one is more stronger. That means analytic function in a domain. That means instead of a single point, we are considering any arbitrary point in that domain, and we are concluding that the function is different analytic at each and every point in the domain. That means corresponding to each and every point which are there in the domain, we can construct a neighborhood, and the function is differentiable at all these points in that neighborhood. Then compared to that, this one is more stronger. That is the entire functions. That means in the first case, we are considering that the function is analytic only one point. Here we are considering that the function is analytic in some domain. Here we are considering that the function is analytic in the entire complex plane. That means we are choosing the eigenplane Z, and if we pick any complex number at that point, the function will be analytic. So that is called as the entire function. So then we'll be discussing what do you mean by the singular point. Singular point means the points where the function is analytic. If a function is given to you, it may happen that at some points the function is analytic, and some other points the function is not analytic. So the points where the function is not analytic is called as the singular point. So if a point z0 is not a point where the function is analytic, so obviously it will be it will be a singular point. Now, how to check whether a given function is analytic or not? So for that, we need to know the Cauchy-Riemann equation or CR equation. So what is the CR equation? So whenever we are considering the function of two variables, the function of two variable means z equals to fxy. So there you know that there is only one dependent variable z and two independent variables x and y. So in order to measure the rate of change of the dependent variable with respect to two independent variable, we get there two partial derivatives. One is del z del x, another is del z del y. Since there is only one independent variable and two independent variables are there. Now, while we are considering the function of complex variable, then here the independent variable z and dependent variable w, both being the complex numbers, have two parts. Z has two parts. The real part is x, imaginary part is y, and w has two parts. Real part is u, imaginary part is v. So here there are four variables, two dependent, that is u and v, and two independent, which are x and y. So how many partial derivatives here we will be getting or will be obtaining? Can anyone tell me? How many total partial derivatives we will be getting here? Have you understood what I am saying?
Sir, please repeat once more.
Okay. Just can you see the blank screen?
Yes, sir.
Okay. So while we are considering the function of function of one variable y equals to fx, so number of dependent variable 1, number of independent variable 1. So we can measure the rate of change of the dependent variable y with respect to independent variable by doing the ordinary differentiation. And here there are only one derivative up to first order. So whenever I am considering the function of two real variable, so number of dependent variable is 1 and number of independent variables are 2. So here we are getting two partial derivatives. One is del z del x, and another is del z del y. Since there are two independent variable, one dependent variable, so we can measure the rate of change of dependent variable with respect to each and every independent variable. So there will be two instances. Now whenever we are considering the function of complex variable fz equals to w, so here z is x plus iy and w is u plus ib. So both being the complex numbers are two parts. So we can write this as x comma y equals to u comma v. So here number of dependent variables are two. These are dependent variable, and number of independent variable are also two. Okay. So dependent variable 2 and independent variable 2. So how many total partial derivatives here will be getting?
So 4.
4 partial derivative, because there are two dependent variable. So each and every dependent variable will be changed with respect to the independent variables. So here we will be getting 4 partial derivative: del u del x, del u del y, del v del x, del v del y. So if a function is given in such a way, a complex valued function fz is defined in such a way that del u del x equals to del v del y and del u del y equals to minus del v del x. So if these two conditions are satisfied, so there are total 4 partial derivatives. So if 4 partial derivatives satisfies these two equation, then it is said that the function is satisfying the Cauchy-Riemann equation or CR equation. So just I am giving one example. Let us consider a function of two variable fz equals to w by z square. So z square means we can put x plus iy. So if you segregate the real and imaginary part, you will be getting x square minus y square plus I into 2xy. So this is our u, the real part, and 2xy is our imaginary part. That means xy is x square. 2xy. So just we need to check whether these two equations are satisfied for this given function or not. If it is satisfied, then we will be saying that the function is satisfying Cauchy-Riemann equation. Otherwise, the function doesn't satisfying function is not satisfying the Cauchy-Riemann equation. So what will be del u del x? What will be del u del x? U is this. So what is del u del x?
Sir, 2x
2x. Del u del y?
minus 2y.
Minus 2y. Del v del x?
2y.
2y, and del v del y is 2x. So here del u del x equals, sorry, del u del x equals to del v del y, and del v del x equals to minus del u del y. So this equation is satisfied. Del u del x equals to del v del y, del u del x equals to del v del y, and del u del y equals to minus del v del x. These two are satisfied. So here the function that is originally defined as this is said to be satisfying the Cauchy-Riemann equation. Okay. Is that clear? Have you got it?
Yes, sir.
Oh. Okay. Then we'll be studying what is the necessary and sufficient condition for a function to be analytic. Before that, just tell me, what do you mean by the necessary and sufficient condition? Have you heard this before? Because I know in the first semester you must have heard this. So what do you mean by the necessary and sufficient condition? Can anyone tell me? Otherwise, I'll give an example. Do you know?
I don't know, sir.
Okay. So you have studied actually.
Forgot.
Okay. So I have studied the rules theorem. So do you know whether have you heard while you have studied rules theorem in first semester whether it is necessary or sufficient? Hmm? Can you remember? Okay, you don't remember. So just someone please tell me what is the rules theorem? I have studied in first semester. Also in class 12 we have studied this.
F of A equal to F G of equal to F of G.
Sir, there will be one point in the range there dy by dx is equal to 0.
In Rolle's theorem, it states that f of x should be continuous in the closed interval AB, and f of x is differentiable in open interval AB, and f of A is equal to f of B. So these are the sufficient conditions, but not necessarily that only these conditions can imply Rolle's theorem.
Okay, so necessary and sufficient condition means let us consider there are two conditions, A is one condition and B is one condition. So assuming that A holds, one condition may be A holds. If this implies B holds, this may be a case. Or secondly, B holds. This maybe implies that A holds. So if B holds, then if it implies that A holds, then it is called as a sufficient condition. Similarly, if whenever A is holding or whenever A holds, if it implies that B will also hold, that is called as the necessary condition. Just I am giving example for Rolle's theorem since we have studied this. So there are two criteria in Rolle's theorem. One is, let us consider f is a function defined in closed interval AB to the set of real numbers R. And there are two conditions. One condition is, let's say f dash c equals to 0. And other two conditions are, number one, f is continuous in closed AB, f is differentiable in open AB, number three, fa equals to fb. Okay, is that clear? F is continuous in closed AB, f is differentiable in open AB, f equals to fb, another is the f dash c equals to 0. Now, if these three holds, then f dash c equals to 0. That means f dash c equals to 0 if this holds. So that is a condition A, that is a condition B. Now B implies A, that means this thing. So it is a sufficient condition. Now just tell me whether the reverse is always true. Reverse is always true or not. That means if this holds, will these three conditions will be satisfied always or not?
No.
No, because if f dash equals to 0, obviously f is differentiable, so f must be continuous, but fa may not be equals to fb. So this doesn't imply that all these three conditions. So it is not necessary. So Rolle's theorem is sufficient but not necessary. Have you understood now? What do you mean by the sufficient and necessary condition?
Yes, sir.
So similarly here also, we'll be studying what are the conditions for which the function f is analytic. So one condition is that f is analytic, and here there will be some other cases or some conditions. So f is analytic if this condition holds. This is called sufficient. Similarly, we know that f is analytic. Then if this condition holds, then it is called as the necessary. So the conditions, whatever we'll be studying here, is necessary as well as sufficient. That means f will be analytic whenever the condition holds. Similarly, f is analytic, that will also imply that the conditions will be valid always. So just let me discuss. Let me share the screen. Okay, so what are the necessary sufficient condition? So these two are necessary sufficient condition. That means let us consider f is a function. We don't know whether it is analytic or not. F is a function that is defined in the form of u plus iv, where z is x plus iy. So if all the four partial derivatives del u del x, del u del y, del v del x, del v del y satisfies Cauchy-Riemann equation, and the four partial derivatives are all continuous, because four partial derivatives will also be functions of x and y, because u, v are functions of x and y. So if we do the differentiation, then the partial derivatives will also be the functions of x and y. Okay. So if this four partial derivatives satisfies the Cauchy-Riemann equation as well as the partial derivatives are continuous, then a function fz will be obviously analytic. That means this, if this holds, then f is analytic. So this is a sufficient condition. And necessary condition means, say function fz we know, and we know that this is analytic. So if fz is analytic, then obviously these two conditions will be valid. That means if these two conditions valid, then fz will be analytic, and if fz is analytic, then also these conditions will be valid converse. So that's why these two conditions as well as the f is analytic are necessary as well as sufficient condition. Unlike the Rolle's theorem, it is necessary as well as sufficient. But Rolle's theorem is always sufficient condition, but the necessary part is not valid. Is that clear?
Yes, sir.
Okay. Is it clear to everyone? If
Yes,
someone
sir.
have, okay.
Do you think any device can transfer it? That case, need to apply some work.
Then derivative of a complex valued function. You know that we can identify the derivative of fz by limit del z tends to 0, fz plus del z minus fz by del z. You know, this is the definition. So by virtue of the partial derivatives, we can identify the derivative of a function. So if fz is a differentiable function, then obviously, so if fz is an analytic function, then obviously it will be differentiable. So if fz is analytic function, then the partial derivatives will satisfy the Cauchy-Riemann equation. So derivative of a function fz is denoted at f dash z, and with respect to the partial derivatives, we can write this in the form of del u del x plus I del v del x. So if we consider the partial derivatives of u and v with respect to x only, now since they are satisfying the Cauchy-Riemann equation, so if we want to convert the partial derivatives in terms of y, then we know that del u del x will be del v del y, and del v del x will be minus del u del y. So by substituting that also, we can convert the derivative in terms of the partial derivatives with respect to y. So this is the definition. So just I am not discussing here. So how to get this result, but you can remember the derivative of complex valued function can also be identified by these partial derivatives also in that form. So if someone wishes to know how to get this result, then you can contact me. I will be discussing it elaborately. But for the time being, you just can remember the result. That means the partial derivatives, by virtue of the partial derivatives, the derivative of a complex valued function can be defined in terms of this. Now I'm discussing one problem. So I think without discussing in the PPT, if I write it notepad, it will be easier for you to understand. Okay. The problem is, let us consider fz, that is e to the power z. So we need to show that this function is analytic. Okay. This function is analytic everywhere, and then find f dash z. So in order to show that it is analytic, we need to use these two conditions. We need to verify whether these two criteria are valid or not. What are the two criteria? The four partial derivatives must be continuous and they must satisfy the Cauchy-Riemann equation. So to show that they are satisfying the Cauchy-Riemann equation, we need to identify the real and imaginary part of that function. So we can write fz in terms of e to the power z by xi by y. Now by using Euler's theorem, we can segregate this cos y so this is our u and this is v. Is that clear up to this? Is that clear or not?
Yes, sir.
Okay. Now we need to find out del u del x. What is del u del x? Del u del x means cos y will be fixed, the derivative of e to the power x with respect to x partially, so this will be e to the power x. Del u del y will be e to the power x will be fixed, derivative of cos y with respect to y partially, that will be minus sin y. Del v del x will be to the power x sin y. Del u del x. So from the partial derivatives we are getting that del u del x will be equals to del v del y and del u del y equals to del v del x. So first condition is valid. That means they are satisfying the Cauchy-Riemann equation. Now we need to show that all these four partial derivatives are continuous for any value of x and y, because we need to show that the function is analytic everywhere. That means for any arbitrary value of z, the function will be analytic. So that means for any arbitrary value of x and y, this function must be analytic. So here, if you put, you know that exponential function is defined everywhere. Similarly, the trigonometric functions like sine and cos is also defined everywhere. So here you know that if you take any arbitrary value of x and y, e to the power x cos y will be defined everywhere for any value of x and y. If you take any value of x and y, this will be defined everywhere. If you take any value of xy, this will be defined everywhere. If you take any value of xy, this will be defined everywhere. If you take any value of xy, this will also be defined everywhere. Okay. So these four partial derivatives are defined everywhere for every value of x and y. So obviously they are continuous, because you know that if a function is defined at a given point, so obviously it will be continuous. So since these four partial derivatives are defined for any arbitrary value of x and y, so obviously they are continuous for any value of x and y. So the two conditions are valid here. The first of all, the partial derivatives are continuous as well as they are satisfying the Cauchy-Riemann equation. So here the function fz that is defined by e to the power z will be continuous.
It requires 1 kilogram of work, 1 kilowatt of work, 1 kilowatt of
Okay. Is that clear? Is that clear or not? Have you understood this? If you have any doubt, you could ask me. Once it is clear, I will proceed to the next problem.
No doubt, sir.
Okay. So I'm discussing the next problem. Oh, then the partial derivative. Sorry. I forgot to discuss the derivative. Then in the problem here, there is mentioned that then find f dash z. So what will be f dash z? So f dash z will be, if you want to find the value of f dash z by using the partial derivative, that will be del u del x plus I del v del x. So del u del x is e to the power x cos y plus I del v del x is e to the power x sin y. So e to the power x cos y plus I sin y. So I sin y e to the power x to the power iy. So e to the power z. So f dash z is e to the power z. So by using the partial derivatives, we can identify the derivative of f dash z provided it is analytic. Because if the function is analytic, obviously it will be differentiable. So the derivative we can actually identify with the help of partial derivatives. So if you do the differentiation of this function directly with respect to z by using the first principle, then also you'll be obtaining that the value of f dash z is e to the power z. Okay, is that clear? Because if you use the first principle or the definition, then also the derivative of fz with respect to e to the power z is e to the power z. So by using the partial derivatives also and using the formula, I can prove that. This one. Okay, is that fine? Is that fine?
Yes, sir.
Okay.
How much weight is 200 step right? Question now, let's understand the question. How is it Now, suppose that
The next problem. So that this function, which is defined by this, can you see the PPT?
now we using electrical energy at the place of electron. Electrical energy
Can you see the PPT? Okay. Show that the function this, which is defined for z is not equals to 0, and the functional value is 0 whenever z is 0. So you need to show that this is satisfying the Cauchy-Riemann equation at origin, but f dash z doesn't exist there. What does it mean? So if we want to show that the function is analytic, then both the conditions must be satisfied. That means the function must satisfy the Cauchy-Riemann equation as well as the partial derivatives must be continuous. So if any one out of these two conditions are not satisfied, then the function will not be analytic. So both the conditions are sufficient. That means both the conditions are required to show that fz is analytic. So if anyone is not valid there, then function will not be analytic. So the function which is given over here, this is obvious that the function satisfies the Cauchy-Riemann equation we need to show. That means although the function satisfies the Cauchy-Riemann equation, not everywhere at 0 we need to show. So although the function is satisfying the Cauchy-Riemann equation at origin, but the partial derivatives are not continuous. Otherwise, the function must be analytic. So f dash z must exist there. So here, this is not happening. That means although the function is satisfying the Cauchy-Riemann equation, but the partial derivatives are not continuous. So if you here separate the real and imaginary part, then real part will be this and imaginary part will be this. So just let me write over here. So the real part is
much time for the content, if I not find any response, then I remove that person from the loop. So that next time I will not say something like that. Right? I mean, I'm just sitting there and I'm just giving the lecture over here. You are not listening, you can unfollow.
so here we need to show that this is satisfying. CR equation in at origin and at z equals to 0. That means the point 0 0
Tell me what is
0 0. But
how I solve this problem. How the electric
so here, if you want to show that this is analytic, this is satisfying Cauchy-Riemann equation at the origin, that means you need to show that del u del x at z equals to 0. That means xy equals to 0 0 equals to del v del y at
okay, thank you. I understood. The first line I
xy equals to 0 0. But if you here directly try to find out del u del x and put x equals to 0 and y equals to 0, then this will not be defined, because if you find out here del u del x, that means x square plus y square whole square, then this is fixed.
what is the price of electricity in this?
Derivative of this will be 3x square minus x cube minus y cube. Derivative of this is 2x. So if you put here x equals to 0 and y equals to 0, you will be getting the form 0 by 0. So if you want to show that the Cauchy-Riemann equation is satisfied at the origin, that means you need to find out the derivative with respect to x and derivative of v with respect to y and put x equals to 0 and y equals to 0. But this is not possible here. So in order to show that del u del x 0 at 0 0 and del v del y at 0 0 equal, so you need to use the definition here. So can you remember the definition of partial derivative? Just I'm writing over here. So if you are asked to find out the derivative at the point AB, so what is the definition? Definition is limit h tends to 0, u a plus hb minus uab by h. Since I am doing the partial derivative with respect to x, so y coordinate will be kept fixed at v, but x coordinate will be getting changed from a to a plus h divided by a. Similarly, del u del y at ab will be limit k tends to 0, u a b plus k minus u a b divided by k. That means here x coordinate is fixed at a, but y coordinate is getting changed from b to b plus k divided by k. Okay. So can you remember this definition? Can you remember this or not?
Yes, sir.
So here we need to use this definition. Similarly, whenever we are finding del v del x, so here just v, u will be replaced by v. So here del u del x means limit del u del x we need to find at the point 0 0. So whenever I am finding del u del x, so x coordinate will be changed from 0 to 0 plus x, y coordinate is fixed at 0 by x. So if you put here x equals to x and y equals to 0, this will be x cubed by x square, so x. So that means this limiting value will be 1. Similarly, del u del y will be limit, this will be sorry, y tends to 0. u0y minus u00 by y. X coordinate is fixed at 0, y is getting changed from 0 to y. So if you put x equals to 0 and y equals to y here, this will be minus y cube by y square. So this will be minus 1. Similarly, del v del x will be 1, del v del y will be 1. So here del u del x at 0 0 is same as del v del y at 0 0, and del u del y at 0 0 is minus del v del x at 0 0. So that's why they are satisfying the Cauchy-Riemann equation. But here, if you find the partial derivatives del u del x, del u del y, del v del x, del v del y, and put x equals to 0 and y equals to 0, they are not defined. Just I have shown. That's why I need to use the definition to find the partial derivatives. So since all the partial derivatives are not defined at the point 0 0, so obviously they are not continuous. Is that clear or not? Although they are satisfying the Cauchy-Riemann equation at origin, but the partial derivatives are not defined at 0 0. So that's why it will not be analytic at 0 0. Is that clear or not?
Not following the Kelvin plan rule of Kelvin equals to then clauses statement very automatically. Similarly, for any heat pump or clauses simply not working.
Have you understood this or not?
Yes, sir.
Okay, so just we can cross verify that by using the formula for derivative. What is f dash 0? F dash 0 means limit z tends to 0, fz minus f0 by z. So fz is defined as this, f0 is 0 given over here, and z is x plus iy. So here we need to find the limit of this quotient. If the limiting value of this quotient exists, then we can say that the function will be differentiable at 0, otherwise the function is not differentiable. So here we can approach towards the point 0 0. So we can approach towards the point 0 0 through the path y equals to mx. So here if I put y equals to mx, so here limiting value will be dependent on x only if I substitute y in terms of x. Now by putting that, if you cancel out x numerator denominator, then the limiting value will become this. That means here limiting value is dependent on m. That means if you change the path, the limiting value will be changed. So the limiting value of this quotient doesn't exist at all. So that's why the function is not differentiable at 0. So by formula also we can show that, because it is satisfying the Cauchy-Riemann equation. But since the partial derivatives are not defined, so they are not continuous. So it is not analytic. So it will not be differentiable at 0. Okay. Similarly, by using the formula for derivative also, we can show the same thing. Okay. So f dash 0 doesn't exist. Is that clear? Is that clear or not? Have you understood this? Just tell me whether you have understood this or not.
Yes, sir.
Okay. Okay, so in the next class, I'll be discussing some more problem on harmonic functions and how to find out the harmonic conjugate. So before that, let me take the attendance manually first, then I'll be sharing the Google form.
And it is not detecting any heat to the room. This device is detecting the single body, single temperature control system. This again, which spectrum? Again, which spectrum? Making landscape. This again, right? Device one is against the all subject is device two. This is taking it to the device and connecting it to a hardware. Taking this value from the device one, device two producing the backward, apply to device two, is getting it to the hardware. They getting it to the hardware. Now, to the here you can see the W. U1 equal to W. When I write for device one, U1 equal to W, there is no other term. U1 equal to W. Okay. Now you see here, U1 equal to 12 plus
So roll number 1, AIML.
Yes, sir.
2. So everyone, while I'm calling the roll number of 1, 2, so others please be prepared, because once I'm calling you roll number, just try to respond at that moment, because otherwise it is very much tough for me. Whenever I have completed taking attendance, then you are asking to provide your attendance, so it is very much tough. So just be prepared. Roll number 2, 3,
Present, sir.
4,
Present, sir.
5, 6, 7,
Present, sir.
8, 9,
Present, sir.
10,
Yes, sir.
11,
Present, sir.
12, 13, 14,
Present, sir.
15,
Present, sir.
16,
Present, sir.
17,
Present, sir.
18,
Yes, sir.
19, 20, 21,
Present, sir.
22, 23, 24,
Present, sir.
25, 26, 27,
Present, sir.
28,
Yes, sir.
29,
Present, sir.
30,
Yes, sir.
31,
Present, sir.
32, 33,
Present, sir.
34, 34, 35,
Present, sir.
36,
Present, sir.
37,
Present, sir.
38,
Present, sir.
39,
Present, sir.
40,
Present, sir.
41, 42,
Present, sir. 41 present. 42 present.
43,
Present, sir.
44,
Present, sir.
45,
Present, sir.
46, 47, 48,
Present, sir.
49,
Present, sir.
50,
Present, sir.
CSBS 1,
Hello, sir. Roll number 16 AIML.
CSBS roll number 1, 2,
Present, sir.
3,
Sir, roll number 1 present, sir.
Sir, 3 present.
4,
1.
CSBS roll number 4, 5, 6,
Present, sir.
7, 8,
Present, sir.
9,
Present, sir.
10,
Present, sir.
11,
Yes, sir.
12,
Present, sir.
13,
Present, sir.
14,
Present, sir.
15, 16,
Present, sir.
17,
Present, sir.
18, 19, 20,
Present, sir.
21, 22,
Sir.
22 present, sir.
23,
Present, sir.
24,
Present, sir.
26,
Sir,
27,
25.
Sir, 27 present.
Sir, 25 present, sir.
28,
Present, sir.
29,
29 present, sir.
30,
Present, sir.
31,
Present, sir.
32,
Present, sir.
33,
Present, sir.
34,
Present, sir.
35,
Present, sir.
36,
Present, sir.
37, 38,
Present, sir.
39,
Yes, sir.
40,
Present, sir.
41,
Present, sir.
42,
Yes, sir.
43,
Present, sir.
44,
Yes, sir.
45,
Present, sir.
46,
Present, sir.
47,
Present, sir.
48,
Present, sir.
49, 50,
Present, sir.
51,
Present, sir.
52,
Present, sir.
Hello, sir.
yes,
Hello.
yes,
Sir, all 15 CSBS. I'm present, sir.
Sir, AIML 12 also, sir.
Sir, AIML 41.
given.
Sir, CSBS 25.
Sir, AIML roll 30.
Just let me share the exam codes in the chat box, then you can. So these are the codes and this is the link. So just click the link and provide your enrollment ID, full enrollment ID and the exam codes and finish the test. So just someone please check from CSBS and AIML and just let me know whether you can access it right now or not.
Excuse me, sir. Did you mark 25 CSBS present? You have skipped my roll number.
It is working for CSBS.
Okay, thank you Arnav. And anyone from AIML?
Sir, roll number 12, did you mark?
Yes, sir. AIML working.
Okay, thank you Rohan.
Sir, roll number 25. Did you mark present?
So if you respond, then it will be marked.
Sorry.
Okay. Thank you all for attending today's class. I'm leaving. Thank you all.